Imagine an artificial intelligence that can master the most complex board games in hours, or a large language model, an AI system trained on vast amounts of text data to understand and generate human-like language that can write functional software code in seconds. Yet this same level of intelligence struggles to reliably fold a towel or pick up a random bolt from a factory floor. This is the current paradox of modern automation. While generative AI, technology that creates new content based on learned patterns, generates entire virtual worlds and processes billions of data points in milliseconds, physical machines remain surprisingly rigid. The assumption that our recent leaps in software intelligence will immediately translate into autonomous, highly adaptable physical machines overlooks a massive engineering bottleneck. The gap between digital brilliance and physical competence is currently costing the industrial sector billions in untapped potential, forcing a stark re-evaluation of how artificial intelligence actually interacts with the physical world. At the heart of this paradox is a powerful paradigm known as reinforcement learning. Reinforcement learning is a type of machine learning where an algorithm learns to make decisions by performing actions and receiving rewards or penalties, essentially learning through relentless trial and error. In virtual environments, this approach has yielded miraculous results. Algorithms have defeated world champions in complex strategy games, optimized massive server cooling grids, and mapped intricate protein structures. These high-profile victories led many executives and engineers to assume that the same trial-and-error architecture would be the ultimate plug-and-play solution for industrial robotics, ushering in an era of instantly adaptable factories. But the physical world is far less forgiving than a simulated chessboard. In a digital environment, an algorithm can fail millions of times per second, resetting instantly to try a new approach without any physical consequence. This luxury of infinite, consequence-free failure is the very fuel that powers these advanced models. When you transplant that same learning mechanism into a 2-ton robotic arm on a crowded manufacturing floor, the rules fundamentally change. The transition from processing digital variables to manipulating physical mass exposes critical flaws in how these systems acquire knowledge. The first major collision between theory and reality is the profound issue of data efficiency. These advanced algorithms require massive, almost incomprehensible amounts of trial and error data to converge on a successful behavior. Generating this data in the physical world operates at the speed of reality, not the speed of a microchip. A robot must physically move its mechanical joints, process visual data through physical camera lenses, interact with a dense object, fail, mechanically reset its position, and try again. What takes a neural network minutes to learn in a high-density server rack could take years of continuous, uninterrupted physical movement. Direct real-world training is simply too slow and financially prohibitive for any commercial enterprise looking to scale operations rapidly. Beyond the sheer time required, the trial-and-error methodology introduces a severe AI safety problem. The algorithm discovers the right way to accomplish a task by exhaustively exploring all the wrong ways first. In a logistics center or an automotive assembly plant, those wrong ways mean shattered inventory, broken robotic joints, and unacceptable hazards to human workers. The cost of a failed physical experiment is infinitely higher than a dropped packet of digital data. A robotic forklift cannot be allowed to crash into warehouse racking 1,000 times just to learn the optimal turning radius. To bypass the slow speed and catastrophic cost of physical training, engineers turned to a logical workaround. They began training algorithms in highly detailed computer simulations, allowing the models to fail millions of times safely before ever touching a physical motor. Inside these virtual sandboxes, gravity, momentum, and friction could be calculated at lightning speed. Once the virtual robot mastered the task, its fully trained digital brain was downloaded into its physical counterpart, theoretically ready to perform flawlessly on the factory floor. This strategy birthed one of the most notorious challenges in modern automation, known as the sim-to-real gap. The sim-to-real gap describes the phenomenon where an AI model trained in a perfect, frictionless computer simulation fails unexpectedly when deployed in the messy, unpredictable physical world. A simulation, no matter how computationally advanced, cannot perfectly account for a slightly worn gear, a microscopic variation in motor temperature, or a subtle shift in ambient lighting that momentarily blinds a camera sensor. Reality is saturated with microscopic variables that software struggles to replicate. When an algorithm optimized for a flawless virtual environment encounters these physical discrepancies, its performance degrades rapidly. A robotic gripper that successfully packed thousands of boxes in simulation might suddenly crush a package or freeze entirely on the actual warehouse floor because the physical cardboard had a slightly different friction coefficient than the digital model. In a high-speed logistics center, a single frozen robot does not just fail a task, it creates a cascading bottleneck that stalls an entire supply chain. These unexpected failures disrupt production lines and erode operational margins, proving that a model's competence in simulation does not guarantee operational success in reality. The echoes of that initial training failure continue to bottleneck widespread deployment across the industrial sector. Even the most advanced robotics companies on the planet must navigate these severe limitations. Consider Boston Dynamics, a company world-renowned for machines that can run, jump, and perform complex acrobatics. While they utilize advanced learning models to help their robots figure out dynamic, fluid movements, they do not rely on them exclusively. Instead, they combine this modern AI paradigm with robust, classical control systems. The underlying architecture relies on traditional deterministic engineering to maintain basic stability and safety, using the learning algorithms only as a highly optimized layer on top to handle specific complex maneuvers. This hybrid approach underscores a critical reality for industrial automation. Factory floors and global supply chains run on predictability, determinism, and absolute reliability. A plant manager does not want a machine that is creatively exploring new ways to weld a car chassis. They want a machine that executes the exact same weld perfectly 10,000 times a day. The exploratory, unpredictable nature of these learning models directly conflicts with the industrial demand for strict operational consistency and measurable output. Recognizing these profound hurdles, the focus of the robotics industry is rapidly shifting toward bridging this gap rather than ignoring it. Companies are investing heavily in highly sophisticated digital twins, utilizing advanced physics engines that inject random noise and controlled chaos into the simulations. By forcing the algorithm to train in a virtual environment that mimics the unpredictable wear and tear of reality, engineers hope to create more resilient models. This technique prepares the digital brain for the inevitable imperfections of physical hardware, ensuring it can adapt to minor environmental shifts without catastrophic failure. This evolution is prompting a fundamental reassessment of how businesses approach physical automation and capital investment. The initial market hype suggested that advanced algorithms would simply be downloaded into generic hardware, instantly creating highly capable general-purpose robots ready to revolutionize labor. The reality is proving that building intelligent physical machines requires a deeply integrated co-design process. The hardware and the software must be developed in tandem, shifting the industry away from a software-first mentality toward holistic mechatronics. Sensors, actuators, and motors must be specifically engineered to communicate seamlessly with the nuances of the learning model, ensuring that the physical machine can actually execute the complex commands generated by its digital brain. For business leaders and logistics operators, understanding the practical limits of these learning paradigms is essential for realistic capital allocation. Investing in automation today requires distinguishing between what works spectacularly in a controlled laboratory and what survives the brutal, unyielding nature of a commercial facility. The integration of advanced learning models into physical spaces is not a simple software update that can be pushed over the cloud. It is a complex, ongoing engineering challenge that requires patience, rigorous testing, and a deep respect for the laws of physics. The ultimate promise of truly autonomous, highly adaptable machines remains a powerful and entirely valid vision for the future of industry. As simulators become nearly indistinguishable from reality and hybrid control systems continue to mature, the physical capabilities of these machines will eventually catch up to their digital counterparts. But until we fully close the gap between the perfect virtual world and the chaotic physical one, the true revolution in robotics will be measured not by what an algorithm can learn in a simulation, but by what it can safely and reliably survive in reality.